Let's start by recalling the arc length formula. What we said was the length of a curve in free space from between two values of t, a and b, is given by this integral. And we sort of justified that this is like a 3D Pythagorean theorem. We drew a little picture to show that in a prior lesson. And there you go. Now, I guess the first thing I'd like to do is just take a careful look at this thing on the inside of the integral. And my first claim is that we can write that in a more compact way. That if you look at this expression here that I've bracketed in blue, that it actually, we know exactly what that is. So if you're not seeing this right away, let me just remind you of something. Generally, our space curves are written r of t equals some function for x with t as a parameter times I, plus some function for y, y of t times j, plus z of t times k. Or you can write that in vector form if you want. You can write it as a vector, x of t, y of t, z of t. So now I claim if you look at this, and then you look at the thing that we're taking the integral of, you might see the relationship. Look what this is. This is the magnitude of r prime of t. Now, if you're not, let's just review quickly why. R prime of t just means we take the derivative of each one of these components, so it becomes x prime of t, y prime of t, and z prime of t. Well, that's not quite what we're taking the integral of, because if you look at the integral is saying the following. Like, for example, you notice that's x prime of t, just like that's y prime of t, and that's z prime of t, but they're also all being squared and then added together, and then we're taking the square root. Well, we know if we take a vector, we square all its components and add them together and then square root that, we're getting the norm. Now, it's sort of nice to look at arc length this way. Because if you think about that for a minute, what that's really saying is that we're adding up all the little lengths of all the tangent vectors. And for each one of those little lengths of tangent vectors, we're multiplying it by a small change in the parameter. So we're sort of adding up the distances that we're tracing along the curve. If you want to think about it this way, I'll try and draw a picture. It won't be so great, but here's your space curve doing whatever it's doing. And at any given point, you can find a tangent vector. So that's telling you the direction and the speed in which you're heading in that direction. But if we just thought about the length of that for a minute, which is what norm r prime is doing, it's saying, hey, how long is that tangent vector? And then we're multiplying it by a small dt as we go from one point to the next point. What we're doing is we're sort of like adding up a bunch of little line segments along the curve. And then we know what integrals do is we let dt go to 0, so you're adding up super, super tiny line segments. They almost start to look like points, and each one of them has a small distance associated with it, and hence you get the total length of the curve from some value, t equals a to t equals b. So let's actually do an example. So here's an example. Consider the helix, the famous helix that we talk about all the time, whose equation is cosine t I plus, we'll say r of t, that is, sine t j plus t times k, and on the interval, we'll do 0 to 2 pi. That's sort of one little rung of the coil, so to speak. We can draw a picture of that. Here's what it looks like. Here's x, here's y, here's z. We know the helix starts at the point 1, 0, 0, and then it goes around from there. We're in the back. So it ends up looking like this. And this point up here at the top is the point 1, 0, 2 pi, after it's gone through 2 pi units of time. So the question I'm asking is that if we could walk along this helix, or we could drive a car along it, and we had an odometer telling us how much distance we traveled, how much distance do we travel? That's what I'm asking. So the answer to that is this. The length of the curve is going to equal the integral from 0 to 2 pi, the norm of the tangent vector. Well, the derivative of this thing with respect to, or the derivative of the x component of the vector with respect to t is going to be negative sine t. And we have to square that, plus the derivative of the y component of this vector valued function is cosine t. We have to square that, plus, and then lastly, 1 squared. Okay, so here we go. That equals the integral from 0 to 2 pi of something surprisingly nice. Okay, if you think about it, this is sine squared plus cosine squared. So that little piece equals 1 plus 1 squared, which is just 1. So this just becomes the square root of 2 dt. All right, so now we go back to Calc 1. Something whose derivative would be square root of 2, that's a function of t, would be square root of 2t, evaluated from 0 to 2 pi. And then lastly, we plug 2 pi in and plug 0 in and subtract. So we get 2 pi rad 2 minus 0 rad 2. Well, that's just 2 pi square root 2. All right, so next what I want you to do is consider the following integral. So I'm going to call this integral the following. I'm going to say s of t equals the integral from 0 to t, the norm of r prime of u du, not dt, sorry. Okay. So this has a special name. You can actually call this an arc length function. Okay? So what this does is it tells us the amount of distance we've traversed along r of t after t units. I guess we'll just say of time, right? We'll just pretend t is time for now, which we usually do. Careful. So just a couple of careful considerations for you to think about. If I said what's s of 5, or even s of 5, what that means is that would say here's your curve in 3 space. Here it is. It's floating through, and maybe we're starting here at t equals 0. And then we go over to t equals 5, a certain amount of distance has been traversed. Right? Now, a couple of things I desire about my arc length function. So for example, if I ask for s of 7, then what I would like is, I would like s of 7 to be bigger than s of 5. Okay? So what am I really requiring? What I'm requiring is that as this thing moves along the curve, whatever this little particle is doing, or whatever, someone following along this curvy road, they never stop, okay, and they never move backwards. So we're just going to move forward the whole time. And that solves a lot of icky problems if we just consider that special case. Okay, it makes sense? Fine. Let's go back to the helix again, of course. And what we're going to do is find the arc length function for the helix. That's what we're going to do. Actually, before we even do that, well, we'll do that. We could do that. That's fine. Okay. So here we go. R of t equals cosine t sine t t. And what we're going to say is we're going to define a function s of t equals the integral from 0 to t norm r prime of u this du. Now we don't have to do much work because we already know that the norm of this tangent vector is always rad 2. So this becomes the integral from 0 to t of rad 2 du. And then that's going to give you rad 2u evaluated from 0 to t. But that's just going to give you rad 2t. So I kind of skipped all the steps there, but I can. So I know that s of t equals rad 2 times t. This is the arc length function for the helix. All right. So now I'm going to do something that's going to seem sort of a little interesting. What I'm going to do now is I'm going to write this just S equals rad 2t. I'm going to solve for t. And if I solve this for t, I get S over rad 2 equals t. Okay? Let's sort of finish this off. So now what I'm going to do is I'm going to create a new parameterization for the helix. I'm going to say, consider a new function, r of s, and it's going to be this. Cosine of s over rad 2 I plus the sine of s over rad 2 j plus s over rad 2 k. And if you think about it, what did I do? I took that equation on the prior page where we had figured out that the arc length was equal to t over rad 2, right? I'm sorry, rad 2t, sorry, my bad. And I had solved it for t. So I ended up with s over rad 2 equals t. So I just plugged that in where all the t's were. Now, if you give this new parameterization a little bit of thought, you'll see it's pretty special. Okay? This parameterization does the following. That if you pick, for example, s equals 5, and you sub that in and find the position of this particle of this object moving along the helix at s equals 5, the distance that it moved along the curve, or the arc length up to s equals 5, is equal to 5. That's what makes this thing special. This is called an arc length parameterization. It has the property that the arc length along the curve up to the particular value of s that you subbed in is equal to that value of s. Okay. So now we've discussed this idea, and you might be thinking, all right, why is this an important idea? Why do we care about reparameterizing a function, a vector function, with respect to arc length? Well, it actually has to do with the idea of curvature, which is something we're going to attempt to define pretty shortly. One more thing we need to just sort of say. We're going to say let capital T of t equal the unit tangent vector. So we know we can find that because if we have a function r of t, we can get the tangent vector by finding r prime of t. Well, that implies that t of t then would be r prime of t over the norm of r prime of t. Okay? So there you go. That's what this is. That's the unit tangent vector. All right. So now what we're doing is we're almost ready to define the idea of curvature. So let me just tell a little bit of a story. Let's pretend we were going to drive along two different roads. A road that looked like this and another road that looked like this. Okay. Well, if you think about it, when we start off on this road at some value of t, we're heading in a particular direction at a particular rate at that time. It's represented by this tangent vector. And then after some time we traverse this road, our tangent vector will have changed direction. And what that means, it means we went through a curve. We experienced some change in our curvature. Well, the same thing would happen traveling along this curve. Okay. So what you'll notice is that it looks like these two vectors here are parallel and that those two vectors are parallel. So someone might say, okay, we've experienced the same change in curvature. But we need to be a little bit more careful because in the example on the left, along this road, I'll trace over in blue, it took us a lot more distance. We had to travel much further along that road to see that change in the direction of the tangent vectors compared to the distance we needed to travel along that road. Okay? So what might we say? We might say, well, this road on the right then has more curvature because in a shorter distance traveled, we see the same change in the tangent vectors. Okay, and that's sort of what the idea of curvature is. We're asking how much does the tangent vector change with respect to the distance I've traveled along that curve. And now you can see I'm talking about distance traveled along the curve and so forth. It means I'm referring to arc length. Curvature can be defined this way. K of t equals the magnitude of the change in the unit tangent vector with respect to our change in arc length. Okay? And if this expansion, if k is small, then what we're saying is we're seeing a small change in the magnitude of the tangent vector with respect to, there you go. Well, that change in tangent vector with respect to change in distance. That would be an example of a small curvature, where if you had k equal to something big, then you'd see something like this. A big change for the same distance traversed. So let's pretend for the time being that that distance and this distance in blue are the same. Maybe it's 1 mile driven along the road, but in this case, after driving 1 mile, I'm almost pointed in the exact opposite direction. But the case on the right, where on the left, I pointed ever so slightly. Okay. So again, to reiterate though, why did we go to the trouble of reparameterizing with respect to arc length? Well, let's just take this road on the left, this small road, the road with small curvature, and talk about what would curvature look like. What if we decided we were going to define curvature as just the rate of change of the tangent vector with respect to the parameter, not with respect to arc length? We have some potential problems, and one of the potential problems we have is that I can drive along this road at any rate I want. So if I decide I was going to drive along this road very slowly, I might notice as I was sitting there watching my clock go by, and then the values of t, the parameter, are increasing, that my tangent vector is changing, but kind of slightly. But then if I drove over the road again really quickly, like in a Ferrari or something, I might notice that, wow, this road feels like it's bending quite a bit. And that's because in less time, I'm experiencing the same change in my tangent vector. So that's sort of the danger. That would be what's wrong with trying to define curvature with respect to the original parameter, t. And that's why instead it's defined with respect to arc length. Okay, just in case you're not comfortable with this idea, let me reiterate one more thing. I'd like you to consider the following. Consider this vector function, t squared, t cubed. I call that r of t. And then consider this function also. I'll call it, this is r1 of t. Let's consider rt of r2 of s, and it's going to be e to the s. Well, I won't use s, actually. I used s for arc length, so I'll use u. E to the u, e to the 2u, and e to the 3u. So first, you might think, oh, these are different curves. Matter of fact, I'm going to give you some values here. I'm going to say that for this function. And for this function, it's going to be 0 less than or equal to u less than or equal to ln2. All right, here's my claim. My claim is actually these two parameterizations trace out the same section of the same space curve. And it doesn't take long to see that. Just take the second thing and let's rewrite it. Let's think of this as e to the u squared and e to the u cubed. A little algebra tells you that that's the same, because if you multiply these exponents together, you would get that. Same thing over here. So this is actually of the same format. You have a parameter, e to the u, that's spanning through all these values. Just like here, we have the parameter t, spanning through all those values. Okay, I should be careful when I sit down here. It's u spanning through the values 0 to ln2. But e to the u you can think of as sort of like a variable also. All right. That said, though, do these things start and end at the same point? Well, that's sort of fun to think about. Plug 1 in the first expression. If you do r1 of 1, you get 1, 1, 1. Oh, that's interesting. Go to the second function, do r2 of 0, which is the starting parameter over here. You get e to the 0, but that's 1. And over here you get e to the 0 squared, which is 1 squared, and then you also get 1 cubed. So they start in the same spot. And then let's consider the endpoints. So suppose you did r1 of 2, you would get 2, 4, 8. If you go down here, you do r2 of ln2, you get e to the ln2, which is 2, and you get e to the ln2 squared, which is 4. And then you get e to the ln of 2, which is 2 cubed is 8. So this ends in the same spot. So these really are tracing out the same section of the same space curve. However, they do not do it in the same amount of time. Notice, the length of this time interval for R2 of u is ln2, or about 0.69. Let's call it seconds for the time being. Up here, the length of this interval is 1 second. Well, what you've shown now is that we've traversed the same curve for the same section, the same total distance, but one parameterization gets it done more quickly. And if you spend a little more time looking at this, you'll notice that the derivatives, you look at the two derivatives, you'll notice that they vary, especially in their properties. It's sort of interesting, especially acceleration. So that's how you can have two different parameterizations for the same space curve and not traverse them at the same rate, which goes back to this idea of curvature. And curvature should depend on something that doesn't vary with respect to the parameterization I chose for that curve. That's why we choose an arc length parameterization, and we define curvature as the rate of change of the tangent, unit tangent vector, with respect to the distance traversed along that curve. Okay? It also should be noted that we don't allow these parameterizations to trace back over themselves. So the curve doesn't do anything like this, where we move forward, stop, go back, and then go forward again. Nothing like that. It's only going to be moving forward. Okay, thanks for watching.